Let's look at derivatives of hyperbolic functions. And since we know the chain rule, we'll also be using a lot of chain rule. For this first function, we have f of x is equal to the hyperbolic sine of the quantity 3 plus e to the 2x. In order to find the derivative of this function, we have to first find the derivative of the outside function. The derivative of the hyperbolic sine of x is the hyperbolic cosine. So we have the hyperbolic cosine of the inside function, which is 3 plus e to the 2x. Then we have to take the derivative of that inside function, which again we'll use chain rule. The derivative of 3 is equal to 0. So we're left with e to the 2x, because the derivative of e to the x is e to the x. And then we need to multiply by the derivative of our innermost function. The derivative of 2x is 2. For this next function, we will need to use chain rule once again. So we have that f prime of x is equal to the derivative of e to the x is e to the x. So we have e to the inside function, which is the hyperbolic cosine of x, times the derivative of the inside function, so times the derivative of the hyperbolic cosine of x. The derivative of the hyperbolic cosine of x is equal to the hyperbolic sine of x. Making sure that we're very careful here, because this is not negative. Hyperbolic functions are a little different from trig functions. Well, the derivatives are a little different. Hyperbolic functions are a lot different. Now we have even more chain rule. We have chain rule inside of chain rule. So now we have f of x is equal to the hyperbolic cosine of the hyperbolic tangent of the square root of x. So f prime of x is equal to the derivative of our outermost function, so the derivative of the hyperbolic cosine of x, which is the hyperbolic sine of x. So we have the hyperbolic sine of the inside function, which is the hyperbolic tangent of the square root of x, times the derivative of the next function, so that'll be the derivative of the hyperbolic tangent, which is equal to the hyperbolic secant squared of the function inside that function, times now the derivative of our innermost function, so the derivative of the square root of x, which is equal to 1 over 2 root x. Curse you, Zoomy laptop. Okay, now we want to find the derivative of the log base 7 of the hyperbolic sine of x. So we have chain rule again. So we have the derivative of log base 7 of x, which is equal to 1 over the inside function, so 1 over the hyperbolic sine of x, times 1 over natural log of 7, times the derivative of the inside function, so times the derivative of the hyperbolic sine of x, which is equal to the hyperbolic cosine of x. To take the derivative of this next function, we will need to use both chain and product rule. So we have that f prime of x is equal to, well, we have this function times this other function. So first we write our first function, so that will be equal to the hyperbolic sine of x squared times the derivative of the second function. The derivative of the hyperbolic cosine is equal to the hyperbolic sine. Then we have to use a bit of chain rule. The derivative of 3x is equal to 3. So that's the first part of our product rule and a bit of chain rule. So we have first function times the derivative of the second function plus the second function. So the hyperbolic cosine of 3x times the derivative of the first function, where we will need to use chain rule. The derivative of our outer function, hyperbolic sine, is hyperbolic cosine. So we have the hyperbolic cosine of x squared times the derivative of x squared, which is 2x. For this last function, not last function, just the last function on the page, we'll have to use chain rule. Luckily, just chain rule. The derivative of our outer function, hyperbolic tangent, is hyperbolic secant squared of our inner function, which is the natural log of x. The derivative of natural log of x is 1 over x. Now for probably the grossest function out of the ones that we need to evaluate. This will be a lot of chain rule. Okay. So we have f prime of x is equal to the derivative of cosecant squared. Oh, let's see. Definitely want to rewrite this. So this function is the same thing as the quantity cosecant of the hyperbolic cosine of the square root of a hyperbolic sine of x, all to the second power. So this will be equal to 2 cosecant of the inside function, which is that hyperbolic. Oh no! This is just a cosecant, not a hyperbolic cosecant. So this is equal to negative 2 cosecant of the inside function, which is the hyperbolic cosine of the square root of the hyperbolic sine of x, times the cotangent of the inside function, which is the hyperbolic cosine of the square root of the hyperbolic sine of x. So that's the first piece, times the derivative of the inside of that cosecant squared. So we have the derivative of hyperbolic cosine is hyperbolic sine of that square root of the hyperbolic sine of x, times the derivative of the square root of the hyperbolic sine of x. So that'll be 1 over 2 times the square root of the hyperbolic sine of x times the derivative of the hyperbolic sine of x, which is the hyperbolic cosine of x. Then finally, we're back to the definition of the hyperbolic functions, which we'll use in order to evaluate limits. So we have the limit as x approaches infinity of the hyperbolic sine of x over e to the x. This is equal to the limit as x approaches infinity of, let's replace that hyperbolic sine of x with its definition. So that'll be 1/2 e to the x minus 1/2 e to the negative x over e to the x. And then much like we were doing earlier when we were evaluating infinite limits, we're going to divide by the highest degree in the denominator, or we can think of that as multiplying the numerator and denominator by 1 over e to the x. So this will be equal to the limit as x approaches infinity of 1/2 e to the x times e to the x will be equal to 1/2 minus 1/2 e to the negative x times 1 over e to the x will be equal to 1 over 2 e to the 2x, and then e to the x times 1 over e to the x is just equal to 1. Now we can evaluate our limit. So as x approaches infinity, this will 1/2 stays 1/2. 1 over 2 e to the 2x will approach 0. Our 1 stays a 1. So this approaches 1/2.